Hello students, this is a review of the Unit 2 practice test. Thank you for joining us today. So question number 1 says that Ms. Wagner conducted a study involving RSG completion and average score on assessments. She found that when students completed no RSGs, the average score was a 3, and when they completed 75% of the RSGs, the average score was a 6. So it asks us to produce a linear model, a linear equation, an exponential model, and an exponential equation. The linear model suggests that we use a table. So let's take a look at this table here. We see that we have a percent of RSGs from 0 to 75, and an average score on assessments going from 3 to 6. Since this is linear, we are going to use arithmetic means. In doing so, we will be able to find the values that belong in these two boxes. So first thing to do when making arithmetic means is to draw our jumps and decide if we are adding or subtracting. Since 6 is bigger than 3, we are going to be adding. In order to find out how much we add, we're going to take 6 minus 3 and then take this answer and divide it by the number of jumps. The answer we get here is our rule. So let's go ahead and fill it in on each of our jumps. And we'll be able to add 3 plus 1 to get 4, 4 plus 1 to get 5, and 5 plus 1 to get 6. We've now filled in the table, and everything's looking pretty great until we get to our equation. Once we start our equation, it asks us to figure out if we want a recursive equation or a explicit equation, and I'm going to say we are always going to want to do an explicit equation because explicit equations can be written for both continuous and discrete. This explicit equation needs a slope and a point. Well, the point's easy. We can find the point by taking any pair, the 0, 3, for example. The slope's where it gets more tricky. We have to decide based on our whole jump from 0 to 75, how far was that? And I can do that by taking 75 minus 0. Equals 75. So this jump is really 75 little itty bitty teeny tiny jumps. And again, we can figure out from 3 to 6, how many jumps was that? Well, that's a 3 space. So our slope is going to be 3 over 75. And if we reduce that by dividing the top and the bottom of the fraction by the same number, we end up with 1/25. So putting this all together, we're going to use point slope form. And that tells us that y equals our point and slope will tell us what to put here. Slope goes first times x minus the x value of the point, and that's right here. That's going to be 0. Okay, that's going to be 0. And then I take the y value, and that's positive 3. So I'm going to add 3. I'm adding because this is an arithmetic sequence or a linear equation. Let's take a look at the exponential model. The exponential model is going to work the same way, except that we need geometric means instead of arithmetic. Remember, to find geometric means, you're taking the last divided by the first, and then raising that to the power of 1 divided by the number of jumps. So if we have 6 divided by 3, I'm going to raise that answer to the power of 1 divided by the number of jumps. In this case, the number of jumps I'm going to start with is going to be 3. 1, 2, 3. And this will make it very easy to fill in the blanks. But later, we're going to have to consider all those 75 little jumps that we saw before to get from 0 to 75. But for now, let's start with the 3 easy to identify jumps. And when I do that, it's going to give me a really weird number on the calculator, and that's okay. That's going to be what I multiply by. You can do it on the calculator because this is approximately equal to 1.26. And I could use that to multiply it through, or I could keep it as the original question. So if I say that this is multiplied by 2 to the power of 1/3, and this is multiplied by 2 to the power of 1/3, multiplied by 2 to the power of 1/3, I'm able to then take my 3 and just write 3 times 2 to the power of 1/3. 3 times 2 to the power of 2/3, because it's the second jump. My exponential equation will work with a different rule. The rule for the exponential equation is going to be a common ratio. And that ratio is 2 to the power of 1 divided by 75. Remember, I'm getting that 75 from the difference between 0 and 75. My point, I'll start with 0, 3. Same point. All right, working here to find our explicit equation, we're going to say that that is y is equal to the value that we started at, 3, times our rule. That's 2 to the 1 over 75. And that rule gets raised to the power of n minus the x value of the point. Now, if I was to simplify this, you would notice that n minus 0, well, that's just n. And when I multiply 2 to the power of 75 to the power of n, it's the same as multiplying 1 over 75 and n. So I can rewrite this. Times n. I could rewrite it still as n over 75. And that's my final answer for my exponential equation. Now, question 2 asks us to think about what would happen if it were a discrete or continuous relationship. Thinking about RSGs, I'm able to decide that I can't complete an RSG if it's not done. So if it's not done and turned in, it's not part of the domain. So this is going to be a discrete model. Other things, like time for your input, would be continuous, since time always is moving. Question number 3 asks us to use the 2 models to predict the score of a student who completed 100% of the RSGs. Looking back at these models, I would use the table itself because the next jump in the table would be that 100. And we just need to know what goes here. Same thing down for the exponential. The next jump gets us to 100. And our question is just what goes in the output section. To find that, all I have to do is multiply by the rule I was using to get the big jumps. That's this rule. So that would be 6 plus 1 is 7, or 6 times 2 to the power of 1/3, giving us 6 times 2 to the power of 1/3. So let's copy those down. 7 from the linear model, and 6 times 2 to the power of 1/3. 4 asks us to compare these to the real average score, which was 7.1. I don't know what 6 times 2 to the power of 1/3 is, so I'm going to type that into a calculator to approximate it. And when I do that, 6 times 2 to the power of 1/3 gives me 7.5595. I'm going to approximate that to about 7.6. So we're looking for number 4, at which one is closer to 7.1. So since 7 is closer to 7.1 than 6.1, or sorry, 7.6 is, the linear model is better. Okay. Question 7 asks us to change from radical form to exponential form. So we're going to remember the same thing, power over root. Power over root is a very useful method of working. I can look at this in a couple of ways, but honestly, I think I want to simplify first. So if I look at this fraction, I have 3 A's on top and 2 A's on bottom. These are going to be canceling, and we're left with 1 A on top. And that's showing us that when I have 2 of the same bases, I can subtract the exponents to show that division over the fraction, basically. So I'm left with an A on top. How about those B's? What happens when I take B to the 7th minus -3? Well, 7 minus -3 is 10. So this becomes B to the 10. And there's nothing left on this denominator. It's just a 1. So I can get rid of it. I have A times B to the 10. In exponential form, that's an A to the 1. So I can rewrite it as A to the 1 over 5 times B to the 10 over 5. And if you wanted to simplify more, you could, it's not required, not for this question at least, continue by doing 10 divided by 5 to equal 2. Either of these answers are correct. Let's take a look at question 8, which is simplify again. Question 8's simplify asks us to find the 4th root of a number times y to the 9th. So I'm going to start with a prime factorization. And I'm going to factor 324 times y to the 9th. And first thing I'm going to do is split this between my coefficient, 324, and my variable, that's y to the 9th. Y to the 9th is really easy to factor. It's just equal to y times y times y times y times y. You get the idea. There's 9 y's there. 324 is more interesting. Since it's even, I'm going to start by taking out a 2. And when I divide 324 by 2, I get 162. That's even again, so I'll try another 2. 162 divided by 2 gives me 81. 81 is no longer even, so I'll try the next number up. 2, 3. What happens when I take out a 3? Well, I'm left with 27. 27's still not even, so I'll try another 3, and that gives me 9, and 9 will factor into 3 times 3. These are my prime factors, as well as all of these y's. So I'm going to rewrite as the 4th root of 2 times 2 times 3 times 3 times 3 times 3. All of that came from these numbers over here, times y, 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 times y. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 y's. Now because I have an exponent of 4, I'm looking for 4 of the same number at a time. I only have 2 here, so I can't circle 2's, but I do have 4 3's. So I'm going to box those. And I have 4 y's. And I have 4 more y's. And it looks like I have 1 y left over. So let's rewrite again. The 4th root of, I have 2 2's, so I can write it as 2 squared. I have 4 3s. I have 4 y's. I have 4 more y's. And I have a single y. Looks like I didn't need all of that extra space over here. Oops. Then I'm going to rewrite again, separating the radical. So I have the 4th root of 2 squared, the 4th root of 3 to the 4th, the 4th root of y to the 4th, the 4th root of y to the 4th, and the 4th root of y. From here, I can notice that I've got some terms that can cancel. Anything that has the same number here and there can cancel, so those cancel, but these ones do not. So I can rewrite again. The 4th root of 2 squared times 3 times y times y times the 4th root of y. Combine the outside terms, 3yy times, combine the inside terms, the 4th root of 2 squared y. And that's going to be equal to 3y squared times the 4th root. 2 squared is 4, so I'll write 4, and y is just y. So I have 4y, and that's my final answer. There. Thank you for listening, and I hope you have a good day.